Welcome back. In this section, we're going to look at the last of the three tools, which is combinations. So we had factorials, which we use if I have a bunch of objects and want to arrange all of them. We have permutations, which are used if I have a bunch of objects and I want to select some of them and then arrange those objects that I've selected. And then I have finally combinations where I have, again, a bunch of distinct objects, and this time I only wish to select them. I don't wish to arrange them. So I'm going to select k of those n objects and not put them in any sort of an order, just choose them. So this is a combination, and there's a couple of different notations for combinations. Just like permutations, we had p n k. Similarly, we've got c n k. And we have this second little notation, which a lot of students mistake this for a fraction, and it's not. So n choosing k in these round brackets. Notice, not like a fraction where there's a little horizontal line. There's no horizontal line there. This is not a fraction whatsoever. It's just a symbol that means a combination where we have n objects and we are selecting k of them. We have the formal definition for what is it. So if you actually felt like calculating a combination by hand, you could, and it's all in terms of factorials. But just like for permutations, that is not really necessary. This formula is not really needed because we do have a calculator function that does the work for us. I mean, if you're interested to know this formula, go for it, but will you ever need it for this class? Not really, because anytime you need to compute a combination, you'll use your calculator. So we had above the number 4, that was factorials, above the number 6, that was permutations, and above the number 5, that's combinations. So C97, combination of selecting 7 things out of 9 things. I would enter that as 9, second function 5, that would give me my combination. There'll be now a little C in your display window, and then 7, so my display window will now say 9C7, and then when I hit equals, it'll give me the answer of 36. So if I had 9 different houseplants and I wanted to select 3 of them to bring outside today, there should be 36 ways for me to do so. Same sort of commentary that I had for permutations. The first number is the bigger one, and it has to be because that's how many things we have to select from, and k is how many things we're actually selecting. So if you wrote 3 choosing 9, that makes no sense at all because that's telling me that you have 3 objects and you're going to select 9 of them, which that's not very possible. 9C3, on the other hand, having 9 objects and selecting 3 of them, that would be possible. So we said for factorials and for permutations, those are cases where order matters, where we're arranging things, where there is some sort of an order in the story that's important to us. For combinations, on the other hand, those are for cases generally where order doesn't matter, where we don't really care what order things are in, or where it's irrelevant what order the things are in. So let's get into using some combinations with a few examples. Example 5 and example 6. Example 5, I've got 30 students in my classroom and there's a very heavy desk that we need to move, so I've decided I need 3 people to help me. So we'll each take one of the 4 corners and lift the table somewhere. So in this case, I just need to pick 3 people. There's not a particular order that I need to pick people in. The desk doesn't have a special corner that I need to slot people into. So I could pick any one of these 4 corners and it really would be just the same. So when we're thinking about this, I'm not going to select my 3 students and then arrange them around the table. I'll select my 3 students and then they can go to the table however they like. And however they like is irrelevant to me. The order in which these people line up at the table does not make any difference to me. So this would be something where I'm just selecting 3 students, not arranging them. So I could say that this is a combination of, out of 30 students, selecting 3 of them. And so easy enough for me to do. And so entering it into your calculator, 30 second function 5, 3 gives you 4,000. 460 possible ways that you can select 3 students to help you out to move this desk. Example 6, I've got 12 different geometry textbooks in the math lab, and I just want to select 4 of them to take home with me. I'm not putting them in any sort of an order, like this one is to be read on Monday, and this one I'm reading on Tuesday, and this one I'm reading on Wednesday. Nothing like that. I'm just picking these 4 books, so it doesn't really matter which gets picked first and which gets picked last. This is not any sort of an arrangement question. This is just a selection problem. So out of the 12 books, I'm just going to select 4 of them. Notice I'm using the other notation for 12C4. Out of 12 objects, I'm going to choose 4 of them, and there's 495 ways for me to do that. Now, we did want to talk for a minute here before we go further about how to decide whether order matters or not, because that's always a question that students have. So when I'm reading a question, how do I know if a factorial or a permutation might need to go in there? Or how do I know if it's only going to be combinations? So the easy answer for this one is, if you're trying to decide if order matters, think about a possible selection that you might be considering and rearrange it, and now ask yourself, is that different? If it is, then yes, the order matters. So an example of that, the Olympic men's hockey team question, where we had 12 teams and we were giving out a gold, silver, and a bronze. We answered that question using a permutation, and I said after we solved that question that order matters for this. So how do I know that order matters? So one option might be Team A gets the gold, Team B gets silver, Team C gets the bronze. And now I'll ask myself, if I changed the order of those 3 teams, would that be different? So would it be different if I gave Team C the gold, Team A the silver, and Team B the bronze? Yeah, that'd be a very different award ceremony for the Olympics. So yes, it does matter what order I pick the teams in. This is something where it wouldn't just be a combination, where it would be a factorial, or a permutation. On the other hand, the desk moving question, if I think about the moving the desks, if I ask Heather, Kara, and Jackson to help me move the desk, would that be the same thing as if I ask Jackson, Kara, and Heather to help me move the desk? The answer is yes. There's no difference between the two, since there's no special positions these 3 people are filling. They're all just grabbing a corner of the desk, and I don't care which corner they grab. So it really doesn't matter what order I select my 3 people in, which is how I know for the desk question, there would not be a factorial and there would not be a permutation. It would just be a combination, because all we're doing is selecting. We're not arranging anything, and we're not arranging because order does not matter. So let's do an example, and for this one we're going to have to tease out for ourselves whether we think order matters or not. So in example 7, we're going to a store where there are 10 brands of chocolate bars, and I am going to be selecting 3 chocolate bars with different brands. So I'm going to select 3 different brands, and now the difference between the questions, in part A, the 3 brands are all going to myself. I'm going to just buy 3 chocolate bars for myself and take them home. B, I'm selecting these chocolate bars and giving them to specific people. So in the first one, let's say one possible way that I could select these brands. So I've got all my different brands, 1 through 10. And let's say I picked brand 1, brand 2, and brand 7. Would that be the same as if I went home with brand 7, brand 1, and brand 2 in my little shopping bag? The answer would be yeah. I mean, that would be exactly the same. In fact, once you put your chocolates in your shopping bag, there'd be no way for you to tell which one was the first one you bought and which one was the last one. So for this one, order does not matter. All I'm going to be doing is making a selection, and out of the 10 chocolate bars, or 10 chocolate bar brands, I will select 3 of them. So 10C3, or 120 different ways for me to do that. On the other hand, for B, if you're thinking about my friends that I'm going to give these chocolates to, there's Mitch, there's Claire, there's Annie. So again, maybe I buy brands 1, 2, and 3. And so maybe I ask myself, if I give Mitch brand 1, Claire brand 2, and Annie brand 3, is that the same thing as if I gave Mitch brand 3, Claire brand 1, and Annie brand 2? It's the same three brands, but it's not in the same order. And I would say these are very different because in one of these, Mitch is getting brand 1, and in the other, Mitch is getting brand 3. These are two very distinguishable kinds of arrangements. So this is not something where I'm just making a selection of chocolate bars. I'm also arranging them. I'm deciding in what order to give them out to my friends. So this isn't just selecting three chocolate bars, it's selecting and also arranging. So this would be P103. I'll select three brands and then I'll arrange them in some sort of order and then give the first one to Mitch, give the next one to Claire, and then give the last one to Annie. And whatever order I put my chocolate bars in, that'll control which one Mitch gets and which one Claire gets and which one Annie gets. So it looks like there's 720 possible options. Now, you could have, if you notice me writing the Mitch, the Claire, the Annie down, we could have gone ahead and done this with the multiplication principle. There'd be 10 choices of chocolate bar brand for Mitch, and then there'd be 9 left because I'm buying 3 different brands. So there'd be 9 choices for what I give to Claire, and then there'd be 8 choices left for what I give to Annie, and we would get exactly 720 things. So the first part is deciding whether order mattered or not. And in A, order didn't matter, and in B, it did. There's something else to notice, which is in B, when the order mattered, we were able to use the multiplication principle. But you might ask yourself, what about part A? What about the multiplication principle there? And a lot of times students would try to use the multiplication principle for part A, and unfortunately, the multiplication principle won't really work when we're thinking about scenarios where order doesn't matter. Because in the case of me making a selection for myself, I can't really say that there's a first chocolate bar and a second chocolate bar and a third chocolate bar to buy. Because once I buy the first, second, and third chocolate bar, once I put them in my shopping bag, there's no way for me to tell which one was first anymore. If I bought brand A, brand B, brand C, that would be exactly the same thing as buying brand C, brand B, and brand A. I'd have exactly the same 3 chocolate bars, even though I bought them in a different order. So, in other words, there really aren't 3 separate tasks. There's actually only one task, and that one task is to select 3 things. In other words, our combination, selecting 3 things out of the 10. So when we get to questions where order doesn't matter, often multiplication principle will not help us out, not at least not easily.